Welcome to our presentation, Neighborhood-Based Hypergraph Code Decomposition. This is a joint work by Nohid Unjum Arafat, Arijit Khan, Orpit Kumar Rai, and Vishwamitra Ghosh. I am Arijit Khan from Aalborg University. A hypergraph consists of a set of nodes and a set of hyperedges. A hyperedge consists of more than one node. Examples include co-authorships in papers, event participant relations in meetups, etc. In this figure, we present four events. T is a tech event, the more popular one. R is a religious event, relatively less popular. And P1 and P2 are social events, the least popular ones. Together with their participants, the participants are nodes and events are hyperedges. Pairs of nodes that co-occur in a hyperedge are neighbors. For example, Annie and Newton are neighbors due to hyperedge R. We study a novel problem of neighborhood-based hypergraph code decomposition. That is, given a hypergraph, decompose it in maximal subhypergraphs or codes such that all nodes in K code have at least K neighbors in that subhypergraph. For example, the 7 code is the hyperedge T since all nodes in T have 7 neighbors. Similarly, the 6 code is formed by the events T and R. We later demonstrate that such K-codes in hypergraphs can be useful in densest subhypergraph extraction, intervening disease propagation, and finding influential nodes for viral marketing. So, what are the challenges in solving our problem? Well, if we use some of the existing methods to solve our novel problem, which is neighborhood-based hypergraph code decomposition, we find improper results. For example, in the literature, there is a method called degree-based hypergraph code decomposition. The degree of a node is the number of hyperedges incident on it. Clearly, the degree and the number of neighbors of a node are different. As a result, degree-based K-code is different from neighborhood-based K-code. In fact, degree-based code decomposition cannot distinguish across these four events. They are all assigned to the same one code. However, neighborhood-based code decomposition can separate them into 7 code, 6 code, and 4 code respectively. One can also consider click graph or bipartite graph representation of a hypergraph and then perform the classic graph code decomposition or distance to code decomposition in a bipartite graph representation. However, those procedures also produce unintuitive results compared to neighborhood-based code decomposition. For example, we see that a new 5 code in this figure based on the classic code decomposition of the click graph of the hypergraph. And in this 5 code was not present in the neighborhood-based code decomposition. We also find two nodes, Poppyden and Wallace in this 5 code since they have 5 neighbors. However, since Hall is not present in this 5 code, so actually the entire hyperedge P2 cannot exist in this 5 code. As such, Halgar and Poppyden cannot be neighbors when considering this 5 code, making Poppyden has less than 5 neighbors in this 5 code. So this is a problem, and such problem arises when we consider the click graph representation of the hypergraph and then we perform the classic code decomposition on this click graph. There are also challenges in adopting graph code decomposition algorithms for our neighborhood-based hypergraph code decomposition. For instance, in the classic peeling paradigm for graph code decomposition, when a node is peeled or deleted, the degree of its neighbors are decreased by 1. This allows various efficient optimizations. In case of our neighborhood-based hypergraph code decomposition, when a node is deleted, however, the number of neighbors of its neighboring nodes can reduce by more than 1, thereby requiring more expensive computation to find the new number of neighbors for a deleted node's neighboring nodes. Next, local algorithms are very effective to implement parallel scheme for graph code decomposition. They are based on H-index. In graph code decomposition, every node with code number k has H-index at least k. And the subgraph induced by nodes with H-index at least k has also at least k neighbors per node in that subgraph. However, the latter property does not hold for neighborhood-based hypergraph code decomposition. In this figure, the H index of node A remains 3 since it has 3 neighbors with H indexes 3 or higher. However, A is not in 3 core, but this is in 2 core. The problem arises because when the node B, which is in 2 core, is deleted, A and E are no longer neighbors since the red hyperedge is not present anymore due to the deletion of B. This makes applying local algorithm challenging and incorrect for our problem. Given such challenges, our problem is how to accurately and efficiently compute neighborhood-based code decomposition. We designed 3 algorithms to solve our problem exactly. Our first algorithm is peeling. We remove the node that has the least number of neighbors in the current round, assign it the core number, and then we recompute the number of neighbors for its neighboring nodes. Such recomputation is of course quite expensive, making peeling very inefficient. So indeed, for example, if we know some lower bound on the core number of the neighboring nodes, we may not need to recompute the number of neighbors of them till that lower bound is reached. For example, in this figure, all nodes are in 4 core, while all nodes except X are in 5 core. Now, when we delete node X, node B's core number does not change. However, in the peeling paradigm, B being a neighbor of X, we need to recompute the new number of neighbors of B after the deletion of X. Such recomputation is redundant since B's core number does not change due to the deletion of X. To improve the efficiency of peeling, we propose a new algorithm called ePeel or efficient peeling. The idea is we compute a cheap lower bound on the core number for every node. Then we need to recompute the number of neighbors of a deleted node only if the lower bound of the neighboring node is less than or equal to the core number of the currently deleted node. This saves a lot of redundant recomputation. However, both peel and epeel are essentially sequential algorithms and it is hard to parallelize them. So next, we consider a local algorithm-based approach which can be easily parallelized. In the local algorithm for graph code decomposition, we iteratively compute H-index of nodes based on the H-index of neighbors, and such H-index computation converges to the true core number of nodes. However, this is not true in case of our neighborhood-based hypergraph code decomposition. As shown in this example and discussed earlier, the H-index of node A remains 3 since it has 3 neighbors C, D, E whose H-index remains 3 or more. But ideally, A belongs to 2 core. To solve this problem, we apply a local core correction procedure in our entire local core algorithm. The more details are given in the paper, but the key idea is we keep reducing the H-index of nodes till certain constraint is satisfied. In particular, we consider the subhypergraph induced by nodes A, C, D, E. In this example, the H-index of node A is getting reduced by 1 till the number of neighbors of node A in this subhypergraph is greater than H-index. So we get the correct H-index of A, which is A is equal to 2, and this solves the problem. We show in the paper that the local core algorithm with this kind of core correction converges to the correct core number, and we also provide a convergence time guarantee. We omit the details here due to the interest of time. We also propose several optimization and parallelization techniques to speed up our algorithm. Finally, we consider an extension of our problem, which is called neighborhood degree code decomposition, and these are based on both the neighborhood and the degree constraints of a node. Next, in experiments, we tested our algorithms and baselines on both synthetic and real networks. Our largest dataset is A-minor with about 27 million nodes and 17 million hyperedges. In this figure, we show the effectiveness of our algorithm, in particular, our new core correction technique combined with the local algorithm. If one applies this local algorithm with on hypergraph without core correction, then it converges to incorrect core number, the one that you see for graph H index. However, when the core correction is applied together with the local core algorithm, then we find that the correct core number can be found after a certain number of iterations. This shows the effectiveness of our algorithm. In terms of efficiency, our local core algorithm is the most efficient compared to our other methods and also other baselines. Our OpenMP parallel implementation of local code decomposes a minor hypergraph with 27 million nodes and 17 million hyperedges in only 91 seconds. We also demonstrated applications of our problem in volume dense subhypergraph discovery and propose a greedy approach with approximation guarantee. This approximation guarantee generalizes Charikar's two approximation guarantee for densest subgraph discovery over graphs. We also demonstrate applications of our method in influence spreading and intervention. We show that inner codes produced by our decomposition method contain influential spreaders. Our decomposition produces the best order of important nodes for deleting a limited number of them while causing the maximum intervention in disease spreading. So in conclusion, in this paper, we introduced a new problem, neighborhood-based hypergraph code decomposition, and we also proposed three novel algorithms. We also discussed its application in volume densest subhypergraph discovery and influence diffusion intervention. In future work, we shall continue working on efficient algorithms for neighborhood degree-based code decomposition. Thank you for your attention.